Welcome to our new session of meetings, and I'm sure you're all enjoying the fact that we actually are here. A lot of us, but there are quite a few of us online as well. We're what's known as a hybrid meeting. Our experience with hybriding is still developing, so I hope you'll bear with us if we have any hiccups today. Hopefully we're trying to get this really slick, so that people who are not present with us in the lecture theatre get a very good experience on the web. So hopefully that will work. For those of you online, if you can see me, if you look in the top left of your screen, you should see a small green shield. Okay. Also, my details of my bank account if you want to contribute to them. Anyway, there's a small green shield. That symbol means that you are using the most up-to-date version of Zoom and that it is secure. You know what happens if you haven't got them? Anyway, questions can be asked at the end of the lectures, but as online you'll be muted, please use the chat facility to write down your question. That's at the bottom of your screen. Write down your question, and your question will be read out later by Council Member Professor Steve Miller, who is somewhere here. Just check that he's there. He's over there, ready to read the questions out. Okay, if you're in the audience and are going to ask a question after one of the lectures, can you please make sure that you wait until the microphone is with you? It's impossible for people on the web to hear unless you've got the microphone. So make sure you've got the microphone before you ask your question. Okay, well, I'm very happy to introduce for our first talk this afternoon the winner of the Michael Penston Thesis Prize 2020, Jennifer Chan, who's going to talk to us about probing the evolving universe with confidence. I always like to see that. All-sky radiative transfer and characterization for cosmic structures. She's a joint Canadian Institute for Theoretical Astrophysics and University of Toronto Arts and Science postdoctoral fellow. She got her PhD from Mullard Space Science Laboratory and an MSc in Astrophysics from University College London before moving to Canada. She completed her bachelor's degree in physics from the University of Oxford, very impressively with a full scholarship by the Benenden School Hong Kong Trust. So it gives me great pleasure to ask Professor Chan to give her talk. Yeah.
Hello, everyone, and hello, everyone online. I know it's very special that we're here. It's hybrid mode, but it's great to see people in person, face-to-face, and also interacting with people online who can be really far away from UK at the moment. It's a great pleasure to be here, and I'm Jennifer. Today, I really want to engage everyone to think about we live in an expanding and evolving universe, but how do we actually probe it with confidence? And this is a big statement. I would say this is the aim we want to reach, but then we have to do more careful thinking in order to achieve this. So what is shown here? I like using a stick. What is shown here is actually artist illustration of what we think the cosmic magnetic field on large scale look like. And here actually is also an artist illustration of ionized bubble, which I will talk more about it. And when you see something that is an artist illustration, you think about, actually, did we get the observation yet? Or are we still waiting for it to happen? And I will hopefully be able to convince you guys that we are getting towards advances in observational front and also from theoretical front. And how do we actually intersect that? But yes, that actually follows nicely because I want to acknowledge my PhD supervisor who provide me with great guidance. So they're important people in my life story because without receiving all the good education I have and guidance, I wouldn't be able to do it. So Professor Jason McEwen over there, he's my supervisor. I actually got lucky with a trio. So I also work closely with Professor Kim Wang at MSSL and Professor Thomas Kitching. And MSSL is based in Surrey, but it's part of UCL. It's a great place. So it's the place that I got so much support to be able to do PhD research. And now I'm based in Toronto. So I work as CETER and also affiliated with Dunlap. So it's a platform that we theorists can actually often interact with observer. That Dunlap is more focusing on, but we actually do outdoor seminar to fight against the pandemic hit part. And actually, in Canada, you can do research in the cold, in the snow. So I think sometimes actually a pandemic put us to think more about where are we now? And I often think we have three big questions in life. Who are we? Where are we from? Where are we going? And today I hope to put everyone in the perspective of, let's think about the universe on the largest scale and see how it will help us to figure out our three big questions in life. And of course, JWST, James Webb telescopes, have recently given us really beautiful pictures. And I hope when we kind of think about the universe, we also not only see the beauty of it, but the beauty of we are living in this universe. So this is my thesis front page. Everyone can download freely there. But I would say my thesis is a little contribution to how the universe that we're living came into its being today. This is the big grand goal that I really want to address. And it's actually a response to our human curiosity and philosophical quest, really. How the universe acquire its magnetic fields. We know magnetic field is everywhere, but how does it start? And the second question is how the universe began to manufacture stars and galaxies, which I will talk about cosmological reionization, the two aspects of the universe that we will focus. So starting from the big grand picture, we have the expanding and evolving universe. I hope to navigate everyone to think about the two aspects of the universe, magnetism and also reionization, the epoch when the first stars, first galaxy, first quasar form and then appear, and their radiation actually make an impact on the surrounding, ionizing the surrounding, so that nowadays we see a mostly plasma universe. And then I will talk about my PhD sort of development. When we think about how to tackle this big question, how the universe acquires magnetism and how it got reionized, we actually need to think about the cosmic messenger that we receive. So it's actually important that we think about how radiation transport. And I know it's a bit technical, but what it meant is how radiation transport in an evolving and expanding universe. So for cosmic magnetism, we can actually use continuum radiation to probe, and particularly the polarization of it. And for reionization, we're actually using the 21 cm line of neutral hydrogen. There are other probes, which I think we truly need them all in order to tackle the question, but I will focusing on this. And once you get the data, making beautiful maps, you really want to study the patterns there. So how do we actually do a pattern characterization and extraction? And of course, what's next? So this is a beautiful picture, really summing up what our understanding or current understanding of the universe looks like. It's ever expanding and it's actually expanding at an accelerated rate at the moment. So the cosmic microwave background observation really give us a nice and neat picture that universe at one point was neutral. There's not much structure there. But nowadays, we see the James Webb telescope or from Hubble telescope and many actually astronomical images. They're black hole, they're actually stars, galaxy cluster, many different types of structures. So how does the universe go from structureless and neutral to mostly being ionized and filled with all types of structure today? So I hope to put everyone's feet into thinking yourself as if you are the radiation propagating in this universe. So you will encounter stuff along your way, and actually what you encounter is different part of the universe as it continues its expansion. I think the cool, but also very hard part of it is actually there's always a cosmic interplay. So structure formation, evolution of the universe underpin the two key science aspects that I talk about. But at the same time, magnetic field and the reionization of gas also somewhat underpin structure formation and evolution. So there's an interplay there. And therefore, understanding one of it and trying to get the others, I think to having all the dots and then later connecting the dots, that's what we scientists want to do. So one key take-home message, if you forget anything I say, I hope you will take this back home. Apart from running more simulation that we want to do to understand what's the theoretical prediction, accounting for some nonlinear physics that we can no longer do it with pen and paper. And apart from taking more observational data, building more telescope, getting better and better data, and developing more advanced tools, for example, in statistics or thinking about machine learning, so and so, I think a very important part is actually thinking about how information encoded into the cosmic messenger that we receive. So radiation comes to us. We also want to understand how the universe information got encoded into the radiation we receive first. And then we want to do an apple-to-apple comparison. That's the goal. So today, we're thinking about how information encoded to radiation that we receive. The universe is magnetic. Because I know it's a broad audience, I want to have everyone also thinking about, oh, we are on Earth, it's magnetic. But actually, on our sun and also galaxy, and even galaxy cluster, they're showing also magnetic activities. However, what we don't know too much about is on the large scale, on galaxy cluster scale and beyond, the cosmic web. We don't know the properties of the magnetic field there. So the big question about cosmic magnetism are what are the properties of this large-scale magnetic field, even at present day? How did magnetic field co-evolve with structure formation and evolution? As I mentioned, the universe is always evolving. So how does magnetic field, the invisible magnetic field, co-evolve with this? And what are the origins of this field? Is it cosmological? Is it astrophysical? Is it the galaxy or stars that really make this magnetic field? Or was there magnetic field in the beginning of the universe to start with? There's some observational front, and we can see really huge advances in there. Back in 1997, people kind of probe or measure polarized sources. We're still talking about 500, on the order of hundreds. Then we can see back in 2009, it's really a big jump. And over 2012, we can also see another jump. But then now we are seeing it more increasingly. How about currently and in the future? So the game changer telescope is what's called the SKA, the Square Kilometre Array. And it will actually take in million of extragalactic polarized source. And why we need to look at polarization is because for all this type of magnetic field in diffuse medium, polarization offers us a way. I will talk more about that later. But in the next 5 years, more immediate future, what we can wait for is the POSSUM and the VLAS survey. And again, it is building up, accumulating to the SKA. On the reionization side, we're thinking about the gas and also how does that ionizing sources from the stars, galaxy, and quasar really impact on the surrounding universe. So the question are, when did the first stars, first galaxy, and first quasar actually, when did it form? How did reionization proceed? And we want to know about the morphology of reionization. By that, what I mean is how the bubble that carved out by these ionizing sources percolate and then eventually merge. I will show a video so that it's more interesting to think about it. But also, what are the properties and distribution of these ionizing sources? All this tied down to not only astrophysics, but cosmology on a grand scale. So as promised, I'm showing you one of the state-of-the-art simulation, DISA, or the DECEN, really showing you how the universe evolved over time, which we stand by redshift. And what is being shown there is the neutral hydrogen fraction. And also here is showing the ionizing radiation. You can see, basically you can see all this kind of Swiss cheese sort of structure. Your ionizing sources, radiation being blown out, and eventually this with more sources, then you have all this bubble being overlapped, and then they kind of percolate. And eventually the whole universe is being ionized, but there remains some neutral clumps as well. And here is even more interesting if anyone like coffee or thinking about percolation. What is being shown here is the ionization front. So you can see how the bubble being blown up and eventually overlap. So this is what we think the universe must have happened. If you think about the neutral universe that the CMB tell us it is, and nowadays everywhere is surrounded by mainly plasma. And We get the theoretical picture of it, and reionization can be probed by 21 cm line of neutral hydrogen. The idea is we are looking at reionization. So there must be some neutral gas to be ionized. Of course, there's the universe is mainly dominated by hydrogen. And therefore, we can use a narrow line, the hyperfine line of hydrogen, to look at reionization. So this is a classical plot, a seminal plot, that what we think about the universe actually undergoes or underwent. So we have the dark ages when the first star's first structure is still emerging. Then we have the cosmic dawn when it really appears, and then it's ionizing radiation, ionize the universe. So when we think about the observable using the 21 cm line, we expect there's a kind of an absorption trough, which when we seen against the CMB as the background is colder than that. So we see an absorption trough for both dark ages and cosmic dawn. But when the stars kind of kick in, you have Lyman alpha pumping that really bump up. So we actually see an emission crest. And of the observational front, there's still also many experiments that has already taken data or is going to take data, like the SKA. We have been really targeting two different types of observation. One is called the global signal, which is a sky average of your map. And then the other is the 21 cm fluctuation. Back in 2018, there have been a very heated discussion about whether we actually already see the cosmic dawn absorption trough. Because as I said, cosmic dawn is when the first star really appear. So it would be really cool. We can't look back that far away in the universe using optical light. So 21 cm is our hope. But I think recently with and other experiments looking at global signal, it's really confirming with the sensitivity reaching to what we think. If you see a signal, it would be a confirmation. If it does see, actually ruling it out that the 2018 claim of absorption trough of cosmic dawn is actually not of astrophysical origin. So it's like, but science is really about incremental knowledge. So I think that's an important point to take. We are actually making progress. And of the fluctuation side, I think there are many experiments that I can't talk about today, but I think it's really promising to see a plot like this, that we see the power spectra of the fluctuation, which tell us how much power in different sort of structure at different redshift of your 21 cm signal should be. I can talk more about it if we have time. But I think we are yet to hit a detection of the reionization signal. I think that's the main message. The challenge of it is we have a very bright galactic foreground. We live inside our own galaxy, and we are talking about 10 to the order 4 to 5 brighter than the reionization signal we want to detect. So looking into the early universe, there's a long way to go, but I think we are at the right time to address this question, as all this are showing us we are getting step by step to there. And I think it's now also the time to really think about how do we make good use of the opportunity that SK will present us, because it's the largest and most powerful radio telescope to be built. So for the SK Meet, we can use it for magnetism that I said, and also for SK Low, looking at reionization through 21 cm line. There's also other science cases, but I will keep focusing on the two aspects of the universe that I talk about. And the goal here is really to understand how the universe acquired its magnetization on the larger scale and how reionization proceeded. We sometimes need to be more focused when we do research, otherwise everything is too interesting. And my research really focusing on bridging. How do we go from theory, modeling and simulation to compare with observation, or going the other way around? We want to use observational data to drive out understanding, to test whether that theory is right and whether we are doing something silly. So what I did here is a covariant formulation. And here, when we go out the other way around, we can look at the pattern. But I think a really big research challenge we have is often simplified models are used, although we apply very advanced tool to understand the data. And by that, I will give you some example. In cosmic magnetism, rotation measure have been commonly used as the quantities to analyze or to infer magnetic field quantities. But this quantity itself is derived from restrictive form of how the radiation actually changes over your line of sight. I'll keep it brief, but there are some important radiation process that we need to account for to understand what are we observing. So what happened is for this rotation measure, you basically just look at the physics of Faraday rotation, but you are assuming that the media does not emit, absorb, and Faraday conversion, which changed the linear polarization to circular polarization. You kind of also neglect that. This is usually weaker, which is okay, but is it really okay to think about we switch off the emission and absorption? Also, I will just kind of flick through because I know equation to some is hard, but I will guide you through. So this is our rotation measure quantity here. So what you're actually measuring is from what I show you IQUV, which is the intensity, linear polarization, and circular polarization. You can also measure the polarization angle, the Wi-Fi. But then what people want is, oh, can we jump from the measurement of how the polarization angle change, jump right straight back to infer the physical condition of your universe, the magnetic field properties of your line of sight medium, and also the free electron density. And also there's something that goes into it. It's like for this NE, they actually only account for the thermal population, not the non-thermal one. But at the same time, non-thermal is what giving us a synchrotron radiation that our galaxy actually emit so brightly that we can't see the 21 cm signal that easily. And I also do a cartoon picture. So here, there are clearly 3 different scenarios where radiation can just propagate, for example, our Milky Way, so interstellar medium. But the radiation can also actually encounter some other medium as well. For example, the intergalactic medium, intra-cluster medium, and then of course we never avoid our Milky Way because we live in it. But what if actually the radiation encounter the galaxy cluster first, then the intergalactic medium? So clearly scenario B is different from scenario C here. We really have to think about as if we are radiation that have been reiterated. So order of encounter matters. Just imagine if you go back to this scenario, the properties of your IGN is different from the galaxy cluster. So by the time you get out from your IGN, you have the properties determined by what really happened when you propagate through the IGN. That's set your initial condition as you go through to the next medium. So your observable depends on what you encounter and the order that you encounter. But the current method using a rotation measure, people often think of it as just an additive quantity. Now, then, if it is additive, and then it's also an integral that I show, it integrates over your path, your sight line, your NE and B parallel. So when is it useful? It really lost that handle to track the order of encounter. And now we see a problem, so we need to quantify when it fails as well. And also, when people get the maps, we want to do some fluctuation analysis. And this is the standard equation that people apply, which also use a random walk model. But I think the key thing here is they have to assume your electron, the ionized plasma, is uncorrelated with your magnetic field structure. But when we think about the physics of it, is it truly uncorrelated in realistic scenario? And there's no guarantee that along your line of sight, compared to what you observe on the sky, which is in the perpendicular direction, things actually cross-talk. Like there's no guarantee that what you measure in this direction is the same as what you expect in the image plane. So we really need to think about as severe radiation. And then if we have many, many different radiation, we get a map. But then on your image plane, the perpendicular direction, things can be really different from what is along your line of sight. And of course, magnetic field is a vector quantity. So we have to think about that more carefully. And as I said, Faraday rotation, electron is important, the NE part. So there's some subtlety. Is it contributed by the density fluctuation of your electron, or is it due to the magnetic field fluctuation? So that requires some special or careful thinking. And true signal actually depends on variation temporally as the universe evolves, but also spatially at different redshift, so along its line of sight. And of course, the frequency of the radiation changes due to we are living in an evolving, expanding universe. So it's hard to do it, but we have the handle to do it. So what I did is to derive the cosmological polarized radiative transfer. It's a formulation that is shown here. And you can see we're actually using invariance in physics to do that. I won't talk about the procedures of how I derive it, but I think the important part is actually derived from conservation law of photons number and also the phase space volume. So it has a very fundamental solid theoretical root. And the key finding is now we can actually do any input model we have, but also at the same time create the maps to make unambiguous prediction of if the universe looks like this, how would it be the observation that we are going to measure? And you can also use it to analyze the standard method. And here, what I'm showing is like, it can tell if you do different input model, and this one is actually an unphysical, non-divergence free magnetic field universe. Although you see something the same, but it's actually different input of your universe, but you cannot distinguish with just using the standard method. So with the CPRT2 that I derived, you can now do it. So I think the good promising thing is we can now actually have the two to make sense of things. We know what we put in, we have the right to calculate what we expect. And it gives us the prediction explanation power. For the reionization side, I know time is running short, so I would say what we are trying to do again, we are using 21 cm line. We hope to use the line to track back how the universe look like when it's undergo that major transition from neutral to ionized. What we hope is that with that narrow line, we know exactly where the frequency center. Then maybe knowing the cosmic expansion, if you put a cosmological model, we can actually use it as a tracker of what the physical condition of the universe is if we measure 21 cm line signal is look like that. Then we can kind of do some inference from there. That's the basis. And that's the common equation people have been using in the field for long. And you can see here, it's actually using an optical depth. And then people try to make a so-called light cone to account for the light that can come from the past to reach us, but it's requiring a separate prescription. So I have been thinking about, okay, wait, that's what people have been doing, but are we sometimes missing out on important stuff? Because again, if we think about as if we are the radiation, there are multiple things that can happen. As the universe evolves, you also get stretched as a photon, and then you encounter different stuff along your line of sight, and you also have local interaction with the medium that you change your properties. At the same time, you have stuff that propagate down from before that reach to your frequency. So the challenge of this field is we have both cosmological and astrophysical effect, and they are covering a broad range. So I've been thinking about how do we, what the physical basis of the tomography that I talk about, using frequency to map out a cosmic time, but is it valid all the time? What if there's the line is actually broadened, and as it propagates down the redshift, you have some contamination that will mix the frequency information and the time ordering information. And when will the widely used expression fail? And when we try to do a light cone prescription to compare with what we observe from telescope, are we doing apple and apple comparison? And I'll just jump straight to the conclusion because it's a bit technical, but I would say, unfortunately, we need to account for stuff more carefully. Particularly, we live in a universe that is with the cosmic microwave background CMB photons. So actually, when we do a fresh approach, similar to how I do the cosmological polarized radiative transfer, now I derive one for the 21 cm line. There's stuff that really show up to be, oh no, wait a sec. If there's a line and continuum interaction, things can be a bit different. But what the two can do is, again, you can input a known physical model of your universe, how reionization proceeded. You just think what it might be, and then you just plug it into the line radiative transfer formulation. Then you can basically compute the resulting spectra, and you can track it over redshift. And of course, what we're more interested in is, and now, what do we observe? And can you distinguish between different ionization history? And yes, the answer is cool. But then what we found is like, this is the seminal work by Preacher and then if we do the radiative transfer properly, accounting for the continuum and the line self-consistently and together when it needs to be, the amplitude, the prediction of the signal is different. And it's because the common expression people use do not account for this line continuum interaction, and which is also a redshift dependent stuff. I know it's technical, so please ask more questions afterwards. But there's the subtle radiative transfer effect that I mentioned here. I know the last part of it is about pattern characterization, which is generic too. You can also apply it to any spherical image you have. But to conclude, reionization, crossing the new two we have. I think a very promising stuff is it shows 21 cm line signal is really sensitive to the physics input that you have. And now we can have the right to do a good fidelity, high fidelity template for the maps. Then we can then talk about characterizing the data, applying machine learning or statistical tool on it. And this is the last piece or main development during my PhD is in collaboration of all this amazing guy. And these are the couplet that I constructed. They're on a sphere because we want to look at all sky data. If we want to probe the universe on larger scale, we really need the full sky to tell us that. And we also need to think about if 21 cm line, we're interested in intensity. So it's a spin zero signal. So we can use the top. But for polarization to look at magnetic field, it's actually a spin two signal. So we need the right data analysis to deal with that. And by pattern extraction and characterization, what I mean here is if you input a spherical image, you can use the couplet that we developed to extract the patterns on different scale and different direction. And you can see it really pick out the elongated structure, and that's why it's called couplet. It's a type of wavelet, and it's an exact transform. What I meant is you don't lose information when you decompose your signal, then reconstruct it back. So we are talking about machine floating 0.1. And the computational speed, we also optimize for that. And the cool thing about being a researcher is you can sometimes think of, oh, what if I mix with other development? So on different scale, you can actually use different type of wavelet to pull out different details. And a cool picture is I just randomly download the spherical data for Jupiter. And we know that there are lots of structure for Jupiter. What happens if we do a couplet analysis? You can see that it pull up kind of broad picture, but you can also see it's picking out different sort of scale features and in different directions too. And the UVC gallery, you can also do the same. And you can really see different features got put out by this too. And we want efficient representation. And what we are trying to compare here is the couplet we developed compared to directional wavelet. You can see that you can use a fewer couplet to represent the whole information. In my abstract, I put 3 very technical questions, but I hope it's a well-defined question that I think is important when we do a research. We ask too many questions. We want to make it more well-defined and focused. And I offer kind of 2 new formalism, doing covariant cosmological radiative transfer for different type of radiation to look at 2 sciences. And when we get the data on full sky, then what we can do to understand the data, to characterize it, to understand the pattern being embedded there. And as I said, the take-home message is we really want to think about the information being encoded into the cosmic messenger that we receive. And these are the new toolbox, new vehicle to drive our research and understanding. And this is the global big picture. We are always using this sort of driving wheel to understand the universe. But I think I would want to put not just magnetic ionized universe in the middle. I hope it is the whole unified universe because we live in one universe and it has everything. It is magnetized, it evolved, it expands, but we are living in the same universe. So thank you very much.
Thank you very much. Can I invite questions? I remind you, viewing on the web, to do the questions through the chat. If you're in the hall, wait for the microphone. Question.
Thank you very much for a very information-packed talk. I look forward to seeing the longer version all day, I would think, with all that data. Great. Can I ask you, what's your mental image or the current model for magnetic fields throughout mainly intergalactic medium perhaps? Have they always existed? Where do they arise from? Do the magnetic fields come from objects, the ones you listed, for example, or are they intrinsic in space-time?
Yes, that's a great question. And I think it's still an open question. There are many actually theory proposed for magnetogenesis. So if you think about Maxwell equation, you always need a magnetic seed to kind of let magnetic field evolve. So the question is, how do we create that magnetic seed? And if you think about the situation, if you have kind of charges and relative velocity in your charge and pressure, that can actually create a magnetic field. So actually back in right before recombination, and there's also theory talking about during reionization, that sort of condition can arise to create a magnetic field. But the problem about it is it generates magnetic field. You need to explain two stuff. One is the amplitude of it. The other is the coherence length, the structure of it. So you need to get two in order to nail that, oh, this is the right theory of magnetogenesis. So the problem so far, without my understanding, is that with all this early universe generated magnetic field, the magnetic field strength is a bit too weak. Then to really answer what we think it is today, which is a nano-Gauss in the intergalactic medium. But there's also a very scarce observation evidence of intergalactic magnetic field at the present day. So the nano-Gauss one, yeah, I think that's why we need SKA in that sense. I can talk more about how that nano-Gauss got determined observationally, but I think the whole picture here is still not very, we are not very sure whether it's actually cosmological origin from this early universe generation, or whether it is the later universe, like galaxy, that really kind of stir up your plasma and then generate magnetic field. So yeah.
Richard Ellis.
A very nice talk. It'll be some time before, for the topology of reionization, there'll be the 21 centimeter data you would like to test your code. But we do have the other hydrogen line.
Yep.
Lyman alpha.
Lyman alpha, yes.
And we're seeing already in quasars that there's patchiness there. Yeah. In the IGM. So can your code
deal with Lyman alpha?
Yeah.
Yes. I've been thinking about Lyman alpha a lot, exactly as what Richard said. It's a very good tool also to look into reionization, and we already have data. Lyman alpha probe more like late stage of reionization, whereas 21cm can go a bit further. But I've been thinking about, my formulation is generic for line. So in principle, I can do 21cm, I can do Lyman alpha, but Lyman alpha is much more difficult to do in terms of you have to consider also scattering. You really have to think about like more transition between your atomic level. So I have been thinking about it. I don't think I have like cracked it down yet to say that, oh, this is what we can do. But I think in general, the line radiative transfer formulation is covariant and generic. So this is the current my take to Lyman alpha, but we should definitely take on multi-probes to look at reionization. And Lyman alpha is very interesting, but it's hard.
Okay, do we have one more question? One more at the front here.
To detect cosmological magnetic fields, you're obviously going to have to use very long sight lines. And so, I mean, a little bit picking up on the earlier question here, what about dark matter? I know it doesn't interact with radiation. It can't emit or absorb it. Maybe the answer to this is second-year undergraduate physics, my memories of which are very vague. But does that mean that it actually can't cause Faraday rotation?
For the dark matter part, I think it does invoke some exotic physics to really understand it. For Faraday rotation, it does need an ionized magnetized medium. So I think that really distinguishes it from really inducing Faraday rotation. But
You can get Faraday rotation by putting a block of glass between the poles of magnet, and that's not ionized. Of course, microstructure is full of electric charge.
yes. So I think we need to be a bit more careful. I think it's like what actually going on with that lab setting, and is it truly Faraday rotation or is it actually something else? Because it's actually interesting with new astrophysical data coming through with fast radio bursts. We also see some very interesting circular polarization, not just linear polarization that we talk about Faraday rotation, but then it's what we observe really linking to Faraday conversion that we think the propagation effect would be happening if you have a plasma, magnetized plasma. Yeah, so I think it's like we need more careful thinking, but we can talk about it more because I know it will go down to a bit more detailed stuff.
Very interesting.
Thank you very much. Now it's my very great pleasure to introduce Professor Pedro Ferreira from Oxford University, who's going to give the Gerald Whitrow Lecture. Professor Ferreira is Professor of Astrophysics at the University of Oxford and Director of the Beechcroft Institute for Particle Astrophysics and Cosmology. He studied and worked at Imperial College London, at the University of California in Berkeley, and at CERN in Geneva. In his time, he's been recipient of a Royal Society University Research Fellowship, a Leverhulme Fellowship, and an ERC Advanced Grant. Cosmic ignorance. Delightful to see humility in a cosmologist.
Well, thank you very much for having me here. I'm honored to receive this invitation to give the lecture. I'd like to thank my nominators and the people who chose me. And I'm very happy to see so many friendly faces in the audience. Before I start, I want to dedicate this talk to John Barrow and Graham Ross, who were wonderful colleagues, collaborators, and friends, and I miss them dearly. And the starting point for my talk is I decided to look up Gerald Whitrow, and I found this very interesting essay, a debate with Hermann Bondi, the great Hermann Bondi, one of the figureheads of modern general relativity, was based in the UK, was based at King's College London, in which they discussed whether cosmology, or physical cosmology as it was then known, or as it's known now, is a science. And the basic debate was as follows. Whitrow said that cosmology, the discussion of the origin of the universe and the evolution of the universe, had been going on for the last 2,000 years. It had started with the Greeks even before, but Thales had really kicked it off, and that it had been going on for millennia, that it was riven with opinion and disagreements and based on very little data. In other words, it was not a science like other sciences. Bondi said, no, that's not the situation. He said that actually physical cosmology, as they then knew it, had only been around for maybe 100 years or less, and really kicked off with the expanding universe and Hubble's measurements, which I will come back to, and that it followed the scientific method, and so it was a physical science. So it was this counterpoint between two points of view, which was Whitrow saying that there are too many opinions, too many different theories, and if you recall at that time, the two main theories was the Big Bang theory of the universe versus the steady state, and they were based on fundamental principles, but there was this tremendous disagreement. Now we know that's not the situation today. This is one of the jewels of modern cosmology. This is a map of the cosmic microwave background, the relic radiation left over from when the universe was 300,000 years old. That radiation is very smooth, but it has these small ripples. And if you build an instrument which you point at the sky and measure the wavelength of radiation at a wavelength, measure the radiation at wavelengths between 1 millimeter and 1 centimeter, and measure the intensity in different directions. This radiation obeys a black body, so you can talk about it in terms of temperature. What you find is there in some directions, it's going to be more intense or hotter, and other directions, it's going to be cooler. Very small fluctuations, 1 part in 100,000. And then you unwrap this and you put it on the sphere and you see this. You see structure. You see this large scale structure when the universe was 300,000 years old. We can do something similar if we look at galaxies today. And so we look in the infrared and we put dots down on the celestial sphere everywhere we see a galaxy. Again, we unwrap it here. And what we see is this cosmic structure. We see empty regions, we see walls, we see filaments, and we see agglomerations, we see clusters. We see what people now call the cosmic web. There is this large-scale structure to the distribution of galaxies in the universe. And we have a mathematical model that can link the cosmic microwave background to the distribution of galaxies. And the cartoon is as follows. Something happened early on, and while the universe was expanding, it was very hot, very dense. It was a hot interacting plasma. It cooled down. Protons caught electrons, formed hydrogen atoms. Hydrogen atoms coalesced to form stars. Stars coalesced to form galaxies. Gravity was the driving force behind all of this and formed the cosmic web that we see today. And it's a precise, very well-defined, well understood mathematical model of the universe that gives us this incredibly consistent picture of what's going on. So this is the situation today, but this was not the situation at the time of Whitrow and Bondi. In fact, it's very nicely summarized by what Jim Peebles says when he arrived at Princeton, or when he started working at Princeton. Jim Peebles had a degree in engineering from the University of Manitoba, moves to do a PhD in physics in Princeton, works on atomic physics, but starts looking around on what he should work on. And he looks at cosmology, and this is what he thought of cosmology: a subject with 2 or 3 numbers, a science with 2 or 3 numbers always seemed to me to be pretty dismal. And what did he mean by this? Well, as I said, cosmology had really taken off in the 20s, when some people had taken Einstein's theory of general relativity, worked it out, and said that the universe was expanding. If the universe is expanding, if you look at distant galaxies, they should be receding away from us. The more distant galaxies should recede away from us more quickly than the closer galaxies. Hubble went away and made a measurement and found this signature, the hallmark of an expanding universe. He found that more distant galaxies had bigger recession velocities than closer galaxies, and this is his plot. And so this kicked it off, and you describe that plot. It's a scatter plot, I agree with you, but it's a plot with, you can describe it in terms of the slope of that curve. That's the slope of that curve is called the Hubble constant. This is known as Hubble's law. If you now go to the 1960s, when Peebles arrived on the scene, this was a summary of the measurements of the Hubble constant. And as you can see, you have very, very precise measurements of the Hubble constant and very discrepant measurements of the Hubble constant. And this was one of the numbers that Peebles was talking about. The other number was, for example, if the expansion was accelerating or decelerating, but there was not very much to talk about. Now, the thing that struck Peebles and a number of other people at the time, like Yakov Zeldovich in Russia, Joe Silk who was then at Harvard, and many others, was that there didn't seem to be a link between this big picture of the universe, this big expanding universe, hot primeval fireball which cooled down and expands, and the large-scale structure that we see today, the distribution of galaxies, the distribution of radiation that we see today. 10 years before, Gérard de Vaucleur had basically got hold of the Shapley-Ames catalog of galaxies and laid it out, and just to visualize what it looked like in the sky. And he'd come up with this interesting plot where you see this big structure, what he called a mega galaxy, a very large structure in the sky. People didn't believe this. People thought there's a systematic error in this. There's something wrong with this. Walter Baade or Fritz Zwicky completely dismissed this result. Even Peebles himself didn't think this made any sense. But Peebles, like others, wanted to work out if there was a link between the distribution of galaxies, the large-scale structure of the universe, and cosmology. And so he set to work with a student, Jia Yu, to try and come up with the statistical properties that you would expect in an expanding universe, which was just slightly perturbed, and which obeyed the laws of physics that obeyed statistical mechanics, electromagnetism, atomic physics, all the laws of physics that were then understood. And this is the plot that he produced. And I will be showing plots like this throughout my talk. Basically, the way to understand this plot is on the y-axis, it quantifies the amount of clustering, how clustered the distribution is. On the x-axis is on a given length scale, and it's kind of inverted. So to the left, you have large length scales, and to the right, you have small length scales. And so what this is showing is that on some scales, you should see more clumping. On other scales, you should see less clumping. It has this interesting oscillatory structure, which is, if anything, it's a legacy of that hot primordial universe when it was just an interacting plasma with acoustic oscillations. So there's a lot of physics in there, but this is kind of the first prediction of what the structure in the universe should look like. And of course, all you can do is you can make statistical predictions for what the universe looks like. This is what's known as a power spectrum. Okay, so this was his prediction. He worked this out. It's a beautiful piece of mathematics and physics and computation, and it was totally ignored. It was, if anything, completely speculative. Now, while he was doing this, other people were advancing on other fronts. So one of the things you can do is you can lay down particles and see how they interact gravitationally. And you can pretend these particles are galaxies and just see how they interact under gravitational force. And what you find is if you create these n-body simulations, you evolve them forwards and you see that they start to form structures. The empty regions empty out, clusters start to form, filaments start to join them up. And this is an example of such a simulation with a few particles by Square Kilometre Array in Cambridge, collaborating with Rich Gott and Jim Gunn at Princeton. At the same time, people decided to visit what they could see in the sky. And so to try and go further than de Vauclair, and a number of campaigns to map out the large-scale structure ensued. And this is an example of a map of the distribution of galaxies created by a team at the Harvard Smithsonian. And this is one of the CFA surveys. And what you find is you find these large-scale structures. This is known as the Harvard stick map. And the galaxies tend to align in certain walls and empty in other regions. So cosmology was really beginning to progress forward in a quantitative way. People were beginning to calculate, make predictions, model the nonlinear regime, and improve the data. Now, while all this was going on, something phenomenal was also going on elsewhere. In particle physics, for decades, there had been an abundance of data to do with particles being created in accelerator physics. And people were trying to piece together a mathematical model that could explain how the particles and fields interacted and what were the fundamental particles and fields. And the high point was when Steven Weinberg wrote his model of leptons, where he wrote down an action which described the electroweaker model, which completely described all the particles in the universe. It predicted the existence of other particles. It was a model from which you could calculate cross-sections, interaction rates. You could use it to predict things that would come from accelerator physics. Throughout the 70s, people understood the strong force, and it really was theory. This is what fundamental physics became. You could sit down and you could write a fundamental action which explains the essential ingredients of the universe. Now, of course, this would contaminate other fields. And interestingly, cosmology had something to say. So cosmology, if you look at cosmology and you step back and you think that you have this expanding universe, and if you wind back the clock, you're going towards a situation in which the universe was hotter and denser, higher energies were being probed. People realized that maybe cosmology could say something about fundamental physics. Maybe we could use cosmology as an accelerator in the sky to study what was going on, what happens at very high energies. And the whole that euphoria from particle physics swept into cosmology. People started to try and build, try to understand if they could construct fundamental theories that could explain aspects of cosmology. And two notable examples are in their progress in trying to understand the large-scale structure of the universe. In galaxies, astronomers had cottoned on to the fact that we might need something extra to explain how galaxies evolved. That was dark matter. Other people trying to solve some problems, some conceptual problems in cosmology, had posited that the universe had undergone at very high energies a period of rapid acceleration driven by some fundamental field. So there was this tremendous cross-fertilization between cosmology and dark matter. And as Mike Turner has said, it was the Wild West because people were basically proposing theories, and theories went up and fell down in popularity. This is a plot from a Vatican workshop of a talk given by Avishai Declan, where on the y-axis, you have the popularity of a given theory, and on the x-axis, you have time. And you see that you have theories that come in and out of fashion. For example, you have a theory with a nu, which was the idea that neutrinos could be the dark matter. It came and went. You have the idea that you could explain everything in terms of baryons. That went away. You have the idea that there's some fundamental particle which is very non-relativistic, cold dark matter. It went up and then it went down, and it goes up and then it goes down. Some people proposed very exotic objects called cosmic strings, and that was up and that was going down. And he even said that that would carry on for the next 10 years. This was 1988. So it was very exciting. There were a lot of theories. We go back to Whitrow's statement. There were a lot of opinions. There were a lot of opinions, and the data wasn't good enough. Now, I think a crucial plot is this plot. In 1987, Dick Bond and George Eustathiou, building on what Peebles had done, they worked out what the microwave background, the ripples in the microwave background should look like if we just took the most basic assumptions of physics at the time. And let me point out that there were no observations of the cosmic microwave of ripples in the microwave background. We'd seen the cosmic microwave background in its total intensity, but we hadn't seen any ripples. And so they built this incredibly sophisticated but fundamental model in that it just uses the physics that we know and put it on a computer. As George told me, they would run it overnight on the supercomputer at Cambridge, and they produced this plot. And so let me just explain the plot. On the x-axis, we have angular scales. On the left, we have large angular scales. On the right, we have small angular scales. And then on the y-axis, you have the amount of fluctuations that you see in these maps. Okay, if you see larger spots of a certain size, you have more fluctuations of those scale on that scale. And what you see is on very large scales, it's pretty featureless. It's just, there's really nothing. Then you have the oscillations, those same oscillations, which are an echo from the primordial plasma. And then it's very damp on small scales. It decays away due to dissipative processes during recombination. Now, that would take overnight on a supercomputer in Cambridge. This I run on my laptop in fractions of a second. Okay, it's exactly the same curve. All right, and look at that curve and remember that curve. Again, amplitude of fluctuations on the y-axis. As you go to the left, large scales. As you go to the right, small scales. All right. And I entered the field in around 1991, and this was the situation observationally in 1991. As you can see, these are all upper bounds. There is no measurements of the cosmic microwave background. And I was at Imperial at the time, and I was doing my PhD in quantum gravity. And in 1992, the COBE satellite announced their detection of anisotropies in the cosmic microwave background. And the effect in the field was phenomenal. People finally realized that they had data in the early universe, that they could work with it. It was a pristine data set, and that they somehow could link it with what was going on today. And I was caught up by that euphoria and moved into cosmology. This is the situation in 1997. Now, the COBE points are the points on the left, and I'm not pointing because the people on Zoom can't see. So, on the left, you have the two COBE points. You have clear detections of anisotropies. Through the 90s, there was a gold rush of experiments trying to measure balloon-borne and ground-based experiments, trying to get better detections of the fluctuations in the radiation. And what you see is this scatter plot of measurements, which you begin to see goes up, but there's nothing significant there. I was fortunate to be in Berkeley around the turn of the millennium, where two balloon-borne experiments were launched to try and measure the cosmic microwave background. This is the maximum boomerang experiments. And what you see is you start to see evidence of a peak, evidence of those acoustic oscillations that you see. This is a couple of years later, the next generation of one of those experiments. And then the big beasts came into play. NASA launched a satellite called the WMAP satellite, which made this measurement of the cosmic microwave background, the ripples of that power spectrum. And then more recently, Planck made these measurements, okay? And so what you see is you see this fantastic improvement year after year in our measurements in the data for cosmology. And what makes us cosmologists really arrogant is this, okay? Is the fact that the theory that was predicted by Bondinov-Statue, you tweak the parameters, you improve the code a little bit, passes through the data like that. It's just completely mind-blowing. And it sort of confirms the idea that maybe we can actually use cosmology to do precision measurements of the universe. Okay, just to blow up. Those are the error bars, and that is the theory. Okay, and this is a curve with a few parameters. You have parameters that you can vary, but very few. There's much more information in that curve than the number of parameters that you tweak to fit the model to the data. Okay. And just to give you a pictorial exhibition taken from Le Figaro of how well measurements of the microwave background have evolved, you start with COBE, which was the first measurements. The next one you see WMAP, and you start seeing more resolution, and this is Planck 2013. And that has been the inexorable progress in using the cosmic microwave background to understand the universe. Now, I focused on the microwave background because it is dear to my heart, but I also should mention the other aspects of cosmology that were being developed. The blue part of this is it's observational. It's a number of surveys went on at the time to try and map out the distribution of galaxies in ever-increasing detail and depth. And what you see is each one of those is a different survey. What you see is the structures, the large-scale structures that de Vauclair had already noticed, CFA2 had already found, they're actually there. And for example, that big cluster, that big alignment up there is known as the Sloan Great Wall. At the same time, the N-body simulations that I mentioned were being perfected, the number of particles being ramped up, computers got better. And so this is almost 20 years old. This is the Millennium simulation. And what you have here is a simulation, and how the simulations, if you compare the simulations to the data, they look very similar. In other words, the theory was getting something right. The theory was getting something right. Gotten it right with the cosmic microwave background, and it was getting it right with the distribution of large-scale structure. This program that started in the 60s was working out. Now, if you have a mathematical model that works so well, and this mathematical model has a few free parameters, we can constrain those parameters with the data. And let me give you two examples of that. The first example is we assume that our universe is Euclidean, that space around us is Euclidean, but it doesn't have to be that way. And in fact, it was shown very early on that the curvature of the universe could be very different. It could be Euclidean, it could be hyperspherical, it could be hyperbolic, and that there was no first principles reason for us to choose any one of these. But it turns out with the cosmic microwave background, we can measure the geometry of the universe, because it affects the way that photons flow to us from the surface of last scattering, from the time of recombination, from 300,000 years ago. And the parameter that we normally talk about is this omega k. That omega k is equal to 0 if the universe is Euclidean. It'll have one sign if it's hyperbolic. It'll have another sign if it's hyperspherical. And what you see is that over 20 years, the precision with which we've measured the curvature of the universe has increased 100-fold. In other words, we can now very precisely say that the universe is Euclidean with a small margin of error. Okay, so that's the first example of measuring fundamental property of the universe with cosmology. Another example is that we can say how many baryons there are in the universe. In other words, how much of the normal stuff, atoms and the other things that build up the standard model there are in the universe, because the density of baryons affect how the primordial plasma behaved, how the acoustic waves evolved, and it'll affect the heights of the peaks in the cosmic microwave background. And so again, this is the progress in measuring the density of baryons in the universe. And basically our precision in measuring the density of baryons in the universe has increased by a factor of 20 to 40 over the last 20 years. So these are examples where we're actually doing what people thought you could do in the 1980s, use cosmology to learn something about fundamental properties of physics of the universe. Now, this model has a bunch of parameters, and it turns out that some of the parameters are parameters which were unexpected 50 years ago. The first aspect is you need to posit for some type of initial condition. And it turns out that the type of initial conditions it needs are unusual. They're not thermal. They're not the kind of thing that appear in everyday life. You need some mechanism to generate those initial conditions. And by far, the most popular way of doing that is using inflation. And it's this idea that I mentioned that the universe underwent this very rapid period of inflation, of accelerated expansion at early times. It's not the only proposal, but it's by far the most popular and successful. Another aspect is that you need something to make galaxies form and generate the cosmic web. You need some form of matter which clumps and doesn't interact with radiation. Mathematically, it's enough just to say that there is some stuff there with an energy density, and let's just that energy density evolve. That's all you need to say. Mathematically, that's a well-defined statement. Finally, the last thing is that you need something to make the universe accelerate at late times to fit the data. And again, it's enough for us to say that there is some form of matter, some stuff that behaves repulsively under gravity, which can translate into a negative pressure. And that's enough. That's all you need to do. That's a mathematically well-defined statement, which means that we have a mathematically well-defined statement, that a theory that can predict what we see, but also predicts the existence of these three very interesting things. Now, I've just said there's some stuff there. There's some stuff there. We don't know what it is. We just know that there is some stuff there. And some of it clumps, and some of it doesn't clump and repels under gravity. And that's the model. That's the model that we've come up with. But of course, that's for many people, given what we've understood of the universe so far, and given what we expected, given the development of particle physics in the 1970s, that's not good enough. And I want to elaborate on that. The big questions that are now asked in cosmology is how did the universe begin, which can be rephrased for many people as what led to inflation? What is the dark matter? And what is the dark energy? And I could answer you, well, how did the universe begin? Well, it just underwent an accelerated period of expansion. And that could be the answer. I could say, what is the dark matter? It's just some stuff that clumps. And what is the dark energy? And I could say, it's just some stuff that repels. And that's pretty much like the situation when Einstein in 1905 was looking at Brownian motion. When he was looking at Brownian motion, he came up with a phenomenological model of why the pollen particles were jiggling around. And his phenomenological model is that there was some discrete structure in water built up of molecules. Note that the neutron was only discovered in 1908, and Bohr's atom was only proposed 10 years later. So it was just a speculation. He said there are these molecules, and that these molecules have a certain size and mass. Okay, and that's enough for his mathematical theory of Brownian motion to work. And that was an amazing step. It was an amazing step in that he predicted there's this stuff going on there. Doesn't know what it is, but that's the step. That's the step that he made. It's very much similar to what we're doing now. What we're doing now is we're saying there is something out there. We don't know what it is, but there is something there that explains how the universe is evolving. Okay, but is that good enough? And this comes to the ignorance part of the problem. What do we mean now when we say we want to understand something? We very much, in terms of fundamental physics, it means that we want to be able to write down a complete action where we understand the fundamental what are the fundamental particles and fields that go into this. And this is the summary of the physics that we know, and it is all there. We know that it's quantum physics, so we have to write a path integral with a wave function. In the wave function, we have the exponential of the action. The action has the Einstein-Hilbert action, which tells us how gravity gives us general relativity. It's what gravity does. It has the Yang-Mills term. It tells us how forces behave, the other three forces behave. It has the Dirac equation, or what gives the Dirac equation, which tells us how matter evolves, and it has the Higgs sector, which tells us how leptons get mass. And this is what it means to understand something in fundamental physics. It means writing down a complete and unique set of equations like that. So if we want to answer the cosmological questions, we would want to do that. We'd have to add a line to that action where there would be a bit that would explain inflation, a bit that it would explain dark energy, and then a bit that explains dark matter. So this is the bar that we have set ourselves, given our aspiration that cosmology is part of fundamental physics. Okay. And so how are we going about doing this? And what I'm just going to tell you is what people are doing. I'm not going to advocate for what people are doing. I'm just going to tell you what people are doing, and I'm going to point out worries about what people are doing. Okay. The first thing you obviously want to do is you want to write something down on that line. You want to build models. You want to come up with a model where you can write down the same way that Weinberg wrote the model of leptons. Okay. And of course, people are doing that, and people have been doing that for 40 years. And theorists are very creative and very productive. So this is a list of models of inflation circa 2013. So this is almost 10 years ago, and there are many more now. And all of these models, there is some fundamental principle behind them. They didn't come up with them. They just didn't make them up. They thought of reasons why their model was the right model. So you have to look at them in the belief that these are motivated models, okay? But there are lots of them. You can do the same thing for models of dark matter. There are many models, and this was 5 minutes of just remembering, writing down things that I thought of. And there are models of dark energy. There are many, many models. So there is no lack of models for these three things. The problem is, of course, that all these models have parameters, and that you can vary these parameters. Many of these models can be excluded with current data, but many of them can't, and you can vary their parameters so that you hit the sweet spot that the data is pointing to. And a particularly interesting example is some work that was recently done by some string theorists, friends and colleagues at Oxford. So what is this plot? This is a plot from constraints from the cosmic microwave background on early universe physics. These are two of the parameters that go into the model. On the x-axis, it's the amount of structure in that primordial map, all right? And you can describe it in terms of one number, n, and if n is big, you have more structure on small scales. If n is small, you have more structure on large scales. And what you find is it's very tightly constrained around that value. Okay? On the y-axis, it's the amount of primordial gravitational waves which are generated during that early period. And look at the scale. It's getting better and better. We now have upper bounds at 1 sigma of around 0.06. Okay. Now, these friends of mine decided to look at superstring theory and see what it predicted for inflation. And in particular, I'm just going to focus on the y-axis, right? And just focus on the values between 0 and 0.06, all right? And so they looked at superstring theory, and superstring theory doesn't predict one model of inflation. It predicts tons of models of inflation. In fact, when they ran their code, which very clever used machine learning to explore superstring theory, it found 300,000 models of inflation. Okay. Look at this plot. This plot has, on the y-axis, has R, so the gravitational amplitude of primordial gravitational waves. And on the y-axis, it's the frequency, or in some sense, it's the normalized number of models that you can find with a particular value of R, okay? So what you have to do is, if you really want, what you really should do is you should multiply that x-axis by 300,000. And what you find is in all these bins, you have tens of thousands, hundreds of thousands of models, well, tens of thousands of models, thousands to tens of thousands of models. So even if you were to pin down the value of R with up to some precision, you would always have quite a lot of models to have to pick from to write on your action. You wouldn't be able to write one line. You'd still be talking about a lot of models. So this is one example of the main problem that we're facing is we have no idea what models we should pick or what models the data will point us to. And this is an example of superstring theory. If you look at the other models, you can always vary constants to try and get you the right result. So this is really the fundamental problem that we're facing in cosmology. So how do you go forward? Well, there are people who say the model's got to be wrong, okay? And if that happens, what you do is you try and explore the inconsistency. But I'm just going to look at two inconsistencies. If you remember the Hubble constant, which was measured by Hubble, there was quite a lot of disagreement in the 1960s. Towards the end of the 1990s, there was tremendous agreement. We kind of knew what the Hubble constant was. And what is interesting is 10 years later, people started to disagree about the Hubble constant again. And the disagreement was between people who measured the Hubble constant looking at the expansion rate locally, by looking at Cepheid stars and supernova, and try to figure out that slope of that curve, and people who used the cosmic microwave background, constrained the model from the cosmic microwave background, and then predicted what the Hubble constant would be today. And what they found is that the local people found it to be high, around 73, and the CMB people found it to be low, around 67. And the disagreement, as of today, is pretty large. It's about 5 or 6 sigma. Now, this is a really serious problem, and there are conferences just on this. I was at a conference recently called Cosmic Tensions, in which this was the main topic. Quite a few people think that this is just a systematics problem in one of the data sets. And I think that is the attitude that one normally has when one has inconsistencies, until something else comes, a new angle comes in that shows you that it's right. But this is one of the inconsistencies that's being discussed. The other inconsistency is much milder, and it's but the same idea. So on the y-axis, I have the amount of clustering, and on the x-axis, I have the density of matter. And if you try and measure the amount of clustering just looking locally, looking at how galaxies are distorted or how they cluster, you get the orange set of errors. If you use the cosmic microwave background and forecast forward, evolve it forward and predict what it should be, you get the blue. And at the moment, it's a 2 sigma discrepancy, but I wouldn't be surprised if in the next year or so with the new data sets, that would collapse more. And so again, we have an inconsistency. But the attitude, again, is we have to, let's not jump to conclusions here and throw the model away. We have these inconsistencies. I've been around long enough that I have seen tens of inconsistencies that came and went. When we measured the microwave background in 2000, we found it a very high baryon density, and we were worried about it. It went away. When WMAP measured cosmic microwave background, it decided that the universe had ionized far too early. That went away. And again, there have been these detections that people jump on and say, oh, there's a problem with the standard model, and then they go away. So the data is much better now, but I think we should wait and see. Okay, so these are 2 examples, and there are other examples that I can discuss if you want. So what do? We try and measure better, and this is kind of the way that cosmology is moving forward. We are building bigger and better instruments. And let me just talk about 2 examples. The first example is we want to make a better map of the cosmic microwave background. And so what we do is we build instruments with better sensitivity. And this is a plot of the sensitivity, the raw sensitivity of experiments over time. And what you see is it's a bit like a Moore's law. You had WMAP over there, Planck had got much better. And the idea is that if you make better detectors and you pack more of them into the focal plane, you can get more precise measurements. That's what's being done. This is the Simons Observatory. It's an observatory which is going online soon, based at the Atacama Desert, which the UK is involved in. So this is one thing you do. You just build better instruments to measure the microwave background. The other thing you might want to do is make even better surveys. And what you want to do there is you want to measure more galaxies over more sky. And so you look at more galaxies by going deeper, having instruments that can pick up fainter objects. And so that's the y-axis. On the bottom of the y-axis is brighter. You want to go up fainter so you can get more galaxies. And you want to go wider. You want to cover more of the sky. And that's what I have on the x-axis. You go from very small coverage to large coverage. And the Vera Rubin Observatory, which incorporates the LSST, is doing exactly that. It's pushing up into that corner, and it'll produce these incredible maps of the distribution of galaxies, really quite revolutionary maps of the distribution of galaxies to quite high depths. Okay. Now that's pushing on the observational front. Pushing on the modeling front, we kind of want to suck as much juice out of the data as possible. And in the case of the galaxy distribution, we want to get the large scale structure, but we want to also start getting the smaller scale structure. And the problem is when you start going into the smaller scales, you start facing the problem that other physics come into play, and very messy nonlinear physics. So this is a simulation done by one of my colleagues at Oxford, Harley Katz. And it is of the evolution of the cosmic web over time. And what you see, I hope you see, is that it is not simple at all. It is not just the placid coalescing through the gravitational interaction of particles and galaxies coming together. No, you have supernova going off. You have explosions. There is this highly nonlinear, intricate physics going on, which is forming the distribution of galaxies, which is forming the distribution of galaxies, and is going to affect the final distribution, which we want to use to constrain fundamental physics. Okay, so this is beautiful simulation. And what does this mean? This means that we need to understand physics to an exquisite level, this type of physics to an exquisite level to try and extract the data. The problem is we don't. And this is a plot basically showing that. What we have here is we're taking simulations where you don't include any of this physics, okay? And it's just gravitational. And we're taking simulations where we take gravitational physics plus all the other physics, the explosions and the plasma and everything else, okay? And we divide the one with everything by the one with only gravitational physics. And what you see is that on large length scales, it doesn't really make a difference. But as you come to small length scale, you start to deviate. And the problem is each one of those lines is a different team running a different simulation with a different set of assumptions of what the physics does on those scales, okay? And there's this huge scatter, right, where we're seeing tremendous deviations. We have no idea how to pin this down to the level of precision that we did with the cosmic microwave background when we did that plot. Now, the problem is of these, there's one further thing, which I pointed out in the abstract, which people are doing, which is we now live in the era of machine learning, which is kind of magic. And what is the idea of machine learning? The idea of machine learning is that you build a computer code, you ask it to solve a problem, and it solves it for you, okay? And the idea is then that if you give it some data, and if the machine or the code knows what it's doing, it'll find the clever way of extracting the information that you want from the data, okay? And there are various types of machine learning. This is the cartoon for a neural net. And it does work. So this is an example of work done by some colleagues at Columbia, led by Zoltan Hyman, in which they take a particular type of observation, weak lensing, and they use the normal approach to try and quantify how clustering depends on matter density, okay? And you get the red curves. Then they build a code, machine learning, they use machine learning, build a code which tries to figure out what information in the data do you really need to figure out these properties. And it does spectacularly well. It reduces the error bars tremendously. It reduces the error bars tremendously, but that's what it does. It reduces the error bars. Now, I think the verdict on whether machine learning is the way to go forward is still up. It's an exciting time. But all of these last three things that I've told you about, improving the experiment, improving the modeling, and using machine learning, will reduce the error bars to an extent. But we're still facing the problem that the models that we have are very flexible and prolific. They can basically fit any size of error bar that we come up with. So, and if that happens, if we have more than one theory fitting that, we don't know what the line that we should put in our action is. Okay. There is, of course, a completely different approach, which I call looking under the lamppost, and which we've already been doing for decades. And the idea is that you pick a particular model. For example, you pick a particular model of dark matter, figure out how it interacts with the world, build experiments, and try and look for it. And two notable examples are looking for what are known as weakly interactive massive particles, or neutralinos. We build these massive detectors that just wait for particles to interact. And we've been doing this for decades, and we haven't found anything. So the end result of this might be that we will say that neutralinos can't be the dark matter. And that is progress. We've eliminated that. Another example which is happening now is that there's a very clever idea of using atom interferometry, using cold atoms, and the way that they behave with each other and how they interact with axions to pick signatures of a particular type of dark matter, axions, very light dark matter, which has particular wave-like properties. And it may just be that this experiment for a particular mass range might find evidence, but it might not find anything. And this is a very costly and time-consuming way of doing this, because if you think of my list of models, you have to go model by model, figure out what are the particular signatures that we can look for, and then build an instrument to look for that. Now, the problem is a lot of these models do not have any specific laboratory signatures that we can use. Another idea is we can look up at the skies and see if there's any non-cosmological way to do this. And a particular interest over the last few years has been the idea that if you we now know how to measure gravitational waves, and we can look at gravitational waves emitted by coalescing black holes. Now, the interesting thing about black holes is they're very extreme objects, and as they come together, they lead to a very extreme event. And in some sense, we know that extreme events, interesting things can happen around extreme objects and extreme events. So here's an example. Suppose you have two black holes orbiting each other and coming together. One of the things that we found is that axions will accrete around them. Axions will accrete, these ultralight dark matter candidates will accrete around them, and they will form these accumulations and spiral structures. Now, when the black holes come together, they'll emit gravitational waves, and these gravitational waves will be affected by these spiral structures and by this accumulation of axions. So instead of looking at the large-scale structure of the universe, you look at gravitational waves and look at the features of the power spectrum, the features of the gravitational wave, and see if we can pick out evidence for axions. So, you know, these are examples, but as I say, one has to go down the list one by one, and I put down this endless list of particles, but we may not have the right particle. We may not have the right theory of inflation. We may not have the right theory of dark energy. So, you know, we have to be we're faced with that. So I think the situation is a little bit like what Whitrow said. I do think physical cosmology is a science. Let's put that to bed. But the situation is similar to what Whitrow was discussing in the 1950s, in that there is a lot of opinion, and people that have opinions on what is the theory that explains each one of these problems that we're faced with. Now, the attitude could be that, in fact, we have a really good mathematical model. The description of these things is in terms of stuff, and that's the only way we can describe it. And we can characterize this stuff with better and better precision, but maybe we shouldn't aspire to write down a line below the standard model action which describes this stuff. We just can't do it. We're faced with that limitation. So that's one attitude, and it doesn't invalidate what people are doing. If anything, we're just going to get a very good description of what's going on, and it's very predictive, as we've seen. If we don't want to do this, then I think we need to think very differently. And I have no idea how we do that, because it seems to me that thinking differently often means invoking some kind of physical principle or idea which you can classify as an opinion again. And so I leave with this grand statement by Einstein, which he said after the beginning of the nuclear era, but which I think applies now, and which is, let the people know that a new type of thinking is essential if mankind is to survive and move towards higher levels. And I think I'll end there.
Thank you very much for a very clear laying out of my last 50 years. I think. Remarkable. You built us up and then let us down.
Sorry.
But I think, you know, that's very interesting. So first of all, can we have questions before opinions? So can we start with a question here?
Thank you very much. Very interesting lecture. I'm going to start with an opinion, and that is that in an age of precision cosmology, it seems to me that what we know precisely is our ignorance about what we don't know. Specifically, are we not worried that the theory depends on inflation, and we can't really get that to work properly or find real evidence for it? Dark matter, we've no idea what that is, and dark energy. And yet science should depend on what you can actually observe and measure and build theory on that rather than the other way around. Just a comment, but
Well, look,
you're not worried.
I'm not worried because I used the example of Brownian motion. When Einstein sat down and worked out Brownian motion, he did not know how water worked at a fundamental level, but his phenomenological description was spot on, right? And it was enough just to say that it had certain objects of a certain size and of a certain mass, and that explained. And that was revolutionary. That was a huge step. Years later, people figured out what it was and how water works and how molecules work. But that was a really important step. I look at this in exactly the same way. We have figured out that there is something out there, and we can describe it really well in the same way that Einstein could describe water molecules. We can describe it in terms of a pressureless fluid for dark matter or particles with very high masses, or dark energy with negative pressure. I mean, it's very clear mathematical description. There's no ambiguity about it. The question is, we would like to do more.
Let's not go there. Although the Greeks, some of the Greeks, I think, oh gosh, the Epicureans would be delighted. Doesn't matter what it is, as long as you explain it. Have 10 solutions, doesn't matter, as long as you've got solutions. Right, next question, Steve Eels.
Well, I mean, it's such a brilliant talk. I really haven't got any questions at all, and I haven't got any opinions, but it just seems the only thing I can think of saying is that you kind of drew a dichotomy between two different schools of thought. So one is you have to write down the action. To some extent, seems very reductionist. And on the other hand, you say, well, there's just this stuff that we can't describe, and that seems not right either. So neither way feel totally right. I have no idea what.
I'm just going to correct you, although I think you're right, but I don't. I didn't say there is just this stuff that we can't describe. We can describe it really well. And the question is that level of description enough?
But it doesn't seem enough, but on the other hand, maybe the other thing seems a bit too much.
Right.
Reductionist, but
yes.
It was absolutely fascinating.
I take Mike Cruz next.
Thank you, Pedro, for a super talk. There's another area of science where there are conflicts, and that is between quantum mechanics and general relativity. Do you have an opinion as to whether that is really going to play into these big scale issues?
Well, I'm going to turn your question a little bit on its head, because I was explaining this. I've been thinking about this for a while, this problem, and I was talking to a fundamental particle physicist, and he hadn't, because he doesn't know enough about cosmological data, he hadn't understood that this was, this could be an issue. And he said, but that's a bit like the problem of quantum gravity, in the sense that we can't measure it. We can't. How are we ever going to figure out what's the correct theory of quantum gravity? We have to use some other way of doing it, which is a bit of a concern. The opinions come in. Whether quantum gravity could solve this, some of the theories in the beginning of the universe use quantum gravity. There are these very nice ideas by Vafa and Pratik Agrawal, which talk about an early state, an initial state, which would lead to the properties that we see today. There was a paper by Neil Torok just a week ago, working out finally, he thinks, the correct wave function of the universe, which is essentially quantum everything. So people do look at it under that perspective.
But you have been inviting us to try and write down an action equation
Yes.
to solve the big problem. But if quantum mechanics has got some flaw in it,
yes,
that action equation, doesn't really mean anything.
The problem with that statement is we do know it means something because it works, right? When we look at the standard model, it works, and it works beautifully. So there's something right about it.
Okay. Richard Ellis, please. Far side.
We turn to observations. You had a slide that said measure better.
Yes.
And, take dark energy. At the moment, it's Einstein's dreaded cosmological constant to 3%.
Yep.
So we're about to embark on these ambitious surveys that are going to take 5 years. And I was depressed to find that, many of them are going to bring the error down to, say, 2%. So there was a very interesting review article recently by Offa Lahav and Joe Silk, which was entitled Cosmology, When to Stop. And so my question to you is exactly that. It gets harder and harder to make more precise measurements.
I agree.
And at some point, we have to stop.
I agree. And I think the other way of saying what they're saying is, there's a limit on how well we can measure, really, given the finite resources that we have. Even if we were able to measure down to a precision of 10 to the minus 5, you could still fit models, different models of dark energy to it. It wouldn't say it is the cosmological constant. Apart from all the problems that the cosmological constant has, there would still be this number of theories that would fit it. And so we would still not be completely sure if it was the cosmological constant. So I agree, you're pushing to the first, which is you kind of know it well enough.
Next question. There's one in the back there.
Thank you, Professor. Thank you, Professor. So I have.
Can you speak up a bit?
Can you hear me?
Yes.
Okay. Thank you, Professor. So I have a question regarding there's a plot that you show a multiple total intensity and polarized light. So I was wondering what is the mechanisms for the polarized light, because I'm not sure if this chain of thought is correct, because if the polarized light it's so low compared to the total intensity, then maybe in that wavelength that we use to observe the multiple, maybe we can, maybe in that case, then we know it would suggest that we don't have to really, I mean, the polarized light might not be very important in that wavelength observation, because the total intensity is just way like 2 order of magnitude.
So total intensity is way higher in the polarized light. We've measured this polarized light. And I because I want to keep the talk clean, I didn't show it. But the error bars on the polarized light are almost comparable to the errors on the total. So we've measured that polarization with exquisite precision. And it is, in fact, one of the things we use, for example, to measure, to constrain the amplitude of primordial gravitational waves. This polarized light arises from recombination and the way that quadrupoles generate polarization during a period where it's not very tightly coupled and its radiation is not very tightly coupled with free streaming. It's a very nice bit of math.
Next question down the front over here.
Just following on from John's question. So when do you reach that point when you say, okay, the kind of incremental progress is small enough not to justify any further research? Like where is the field in the thinking right now?
It's nowhere near that, because luckily we've got the next 10 years of surveys which are working. And so we have data. We've already invested it, but it's something we might want to ask ourselves in 10 or 15 years.
Behind you.
Just to comment on that last comment, you're going back to the 1890s where people thought physics was complete.
Yeah, so in the similar kind of vein. So I like the message that shut up and keep measuring better. It doesn't cut it. Great. But I mean, we don't want to stop too soon. So are there measurements that you think would qualitatively change the picture that we might make that would change this so that it's not about measuring things, but lead us in a fundamentally new direction?
To solve the 3 big problems that I put up, I have no idea. Okay. What we do know is that when we start measuring things better and observing the universe more, we discover stuff. Okay. And I've only focused on these 3 fundamental problems, but there's all this beautiful stuff going on, trying to understand the evolution of galaxies, the distribution of gas in the universe. There are all these other physical problems, which I have not alluded to, which are completely valid and which we will learn a lot. The kind of stuff that you work on. I mean, we will learn a lot from from these coming observations. And there are more observations that you can do. Those are more, I think, related to astrophysics than to fundamental physics, which was the focus of what I'm saying. And unfortunately, I have no idea what we should do. I have no idea.
Okay. One last question, maybe? Quick one.
I could shout.
No.
A brief practical suggestion to avoid the risk of ambiguity in the terms we use. It might help at a time when people are talking about multiverses and the possibility of structures outside the observable cosmos. If we use cosmos or observable cosmos for what we've been talking about this afternoon, and reserve the term universe for those structures, not necessarily the whole of the universe, which lie outside the observable cosmos.
Thank you for your suggestion.
I can think another word for it as well, for the stuff outside our universe. Okay. Okay. I think we'll leave it there. I think, as you said, cosmology when to stop. I think we should perhaps stop there. Thank you very much.